Today we are going to start the next chapter of the first unit, electrostatic, and the chapter is electrostatic potential and capacitance. So this chapter is also based upon the concept of electric field. So now let us start this. Let us suppose I am having a system of positive charge. So this positive charge, it will produce some electric field around it. Okay. Now let me consider one more charge, some test charge, and suppose this test charge is placed at some point P, and the magnitude of charge is plus Q. Clear? Now, because both the charges they are having like charges, so that means there will be some repulsive force between these two. So the repulsive force will be along this direction. So which force is this? This is the electrostatic force. Now, if electrostatic force is acting on this charge cannot be at rest. So if this charge is at rest, that means there must be some external agency who is holding this charge at this point. Suppose I am holding this charge at this point. So what if I leave this charge free? If I leave this charge free, will the charge be stationary still? No. It will start moving away from this body. So it will start moving, and what will happen? It will get some kinetic energy. It will gain some kinetic energy. But by conservation of energy, we know energy cannot be created. It means even at this point, when it was at rest, it should have some energy, which energy is being converted in the form of kinetic energy. So that means some energy was stored in this charge when it was at rest at this point P. So that energy, that stored energy in this charge, that energy is called potential energy. So whenever a body is under the influence of some force, so even if it is at rest, it has some stored energy in it, and that stored energy is known as what? It is known as potential energy. Like in case of gravity, suppose I am holding this object. So if there is no electric field, suppose, but still some gravitational field is there, because it is under the influence of gravitation of Earth. So does it have some energy? So let us see. अगर मैं इस object को free छोड़ दूं अभी, so it will fall towards the center of Earth. It means at this point when it was at rest, it was having some energy. और जैसे मैं इसको फ्री करता हूँ, क्या होता है? ये नीचे की तरफ फॉल करता है. इसका मतलब क्या हुआ? इसकी पोटेंशियल एनर्जी किस में कन्वर्ट होना स्टार्ट हो गई? इन द फॉर्म ऑफ काइनेटिक एनर्जी. So that means whenever a body is under the influence of some force, one more example. Suppose we are having a spring. So when spring is stressed and some block is connected with it, so it is at rest, so that means it is not having kinetic energy, but it is under the influence of spring force. So when I leave it free, what happens? The object gets some kinetic energy. It means when it was at rest, it was having some stored energy in it. So that stored energy is known as potential energy. So this concept you have already studied in class 11th as well. Now, so the energy in this charge, it was due to its presence in some electric field. So that means this potential energy in this charge, it is due to some electric field. So this energy of the charge is known as electrostatic potential energy. Is that clear? I repeat this part. I assume one positive charge which is placed at this point. It is at rest with the help of some external agency. Now, if the charge is left free over here, this charge will start moving away from this object due to the repulsive force or due to the influence of electric field of this charge configuration. So if it moves, it means it gains some kinetic energy. So if it is getting some kinetic energy over here, it means it should have some energy at this point, because energy cannot be created. So This stored energy in this charge is known as the potential energy, and because this stored energy is due to the presence of electrostatic field, so this potential energy is known as electrostatic potential energy. Like in this case, this object is having its potential energy due to gravitational field, so we call it gravitational potential energy. Okay, so that means whenever some charge will be in some electric field, it will have some electrostatic potential energy. Fine. So we understood this concept. But now the question arises, we understood that if the charge is in some electrostatic field, it will have some energy. But how much energy does it have? How will you give some value to this? So for this, we are going to have another definition. Another definition in terms of some measurable physical quantity. Okay, so now let us try to understand that concept. To define potential energy in a way so that we can give it a numerical value. That means we have to define this potential energy in terms of some physically measurable quantity. Okay, so let us start. So I am having the same charge, same test charge Q, which is placed at this point P. Yeah. So at this point P, it will be having some potential energy. So let me call it UP. We don't know how much it is. Let me call it UP. Now what I do, I take this charge from point P to some point R. Okay, I move this charge from point P to point R. Okay, so how to do that? For this I have to apply some external force on this charge, and originally which force is acting on this? The electrostatic force is acting on this in the opposite direction of external force. Okay, so now when I will move this charge from point P to point R, I have to do some work. Yes, and when this charge it will be moved from point P to point R, what do you think? क्या potential energy में कोई change आएगा? Of course, there will be some change in the potential energy, because in this case the distance from the original charge configuration, it is getting changed. So that means what will be the change in potential energy in that case? So change in potential energy delta U. So that change can be written as, suppose potential energy at point is UP and potential energy at point R is UR. So that change in potential energy can be written as UR minus UP. But the question is, how much change will be there? Will there be any relation between the change in potential energy and the work done in moving the charge? So the change in potential energy will be final potential energy minus initial potential energy. That means potential energy at point R minus potential energy at point P. Okay. Now, how much will be this change in potential energy? So there is a repulsive force acting on this charge Q, which is repelling this charge in this direction due to this electrostatic force. So if I want to move this charge from point P to point R, what has to be done? I have to apply some force on it. I have to push this charge towards this, isn't it? So when I am pushing this charge and the charge is getting displaced, it means I am doing some work on the charge. So that means the change in potential energy will be equal to the work done in moving the charge from point P to point R. So I can write it as WPR. But remember, this work done should be without acceleration. But why is it so? Let us understand. As we know, when we do some work on the object, that work can be converted in the form of kinetic energy as well. In 11th we used to study one theorem, work energy theorem, work kinetic energy theorem, which states that work done is equal to what? Change in kinetic energy. But we don't want to involve kinetic energy here. We are talking about potential energy only. So for that, what do I need? I want that velocity should not change. There should not be any change in velocity, any change in speed. And if there is no change in speed, it means acceleration should be 0. And acceleration 0 means the net force on the charge, it must be 0. And net force 0, it means there are two forces acting on this charge. One is the electrostatic force and one is external force which we are applying to move the charge. So it means if net force is 0, for that this condition should be satisfied. That electrostatic force, it has to be equal to what? External force in magnitude. Their directions are opposite, but their magnitudes, they must be equal to each other. That is why I wrote that electrostatic force and external force, they must be equal to each other. Okay, so this part is clear to you. Whenever we are talking about the potential energy or change in potential energy, it is already understood that this motion should be without acceleration. And the reason is, if there will be some acceleration, there will be some change in velocity. And then there will be some change in kinetic energy. So that means some part of our work that will be converted in the form of kinetic energy. But we simply want to consider potential energy over here. Okay, and the change in potential energy as the work done by external force in moving the charge from one point to another point without acceleration. So that is how we can define change in potential energy. Okay, now what if I take this point P to be at infinity? अगर इस point P को हम infinity पे assume कर लें, so at infinity, will there be any electrostatic force? No, electrostatic force will become 0. So if at infinity I will leave the charge free, because there is no force acting on this, there won't be any kinetic energy. It won't get any kinetic energy. Like in this case, when I left this charge free over here, it started to move. It started to gain kinetic energy. Okay, due to which we understood that there was some potential energy at this point. But now if the charge is at infinity, there is no force acting on it, there is no electric field there. So that means if I leave the charge free, it won't get any kinetic energy. It means उसके पास potential energy भी नहीं है. So that means when you take the point at infinity, potential energy at infinity, that will be how much? That will be 0. So this infinity is taken as reference. So the common reference in case of electrostatic potential energy, that is taken as infinity. Is that clear? Now, if I use this concept over here, if I use this condition that if the point P is at infinity and I use it over here, then what do I get? I get that UR minus U infinity. As I have assumed that point P is at infinity, so in place of P I am writing infinity, that will be equal to W P. P is at infinity R. But because infinity is the reference, so potential energy at infinity will be how much? That will be 0. So this term will go to 0 only. And then what do we have? We have potential energy at point R is equal to work done. Work done in moving the charge from where? From infinity to that particular point. So this gives us the definition of potential energy. So electrostatic potential energy, how can we define it? We can define it the work done by external force. Work done by external force in moving the charge from where? From the reference. And reference is what? Reference is infinity. From infinity to that particular point. And remember, this has to be done without acceleration. So this is the final definition of electric potential energy, which states that the electric potential energy at a point is the work done by external force in moving the charge from infinity, from the reference to that particular point without acceleration. Hence, mathematically, we can define the potential energy at a point, suppose R. It can be written as the work done in moving the charge from infinity to that point, and it can be written as we know, work done is equal to force into displacement. This work done we have to consider that is due to the external force from infinity up to the point R. As external force and electric force, they are opposite to each other, as we have just seen. So if I will calculate this work done due to the electrostatic force, so that work done will be opposite of this in sign. So that means if this work done is positive, that work done will be negative. So I can write it as that it can be defined as negative of work done by which force? By electrostatic force. So this is the final definition of potential energy. And if we have to write out potential energy difference, delta U, suppose there are 2 points UR and UP, that will be equal to work done by the external force in moving the charge from point P to point R, and in form of integration it can be written as work done by external force in moving the charge from point P to point R. So limit will be P to R. So that is how we can define potential energy and potential energy difference. One more important point we have to see from here. Suppose if I consider this term, so potential energy at point R is work done in moving the charge from infinity to R. So this term states that potential energy at R is equal to work done in moving the charge from infinity to R. Infinity is the initial position, R is the final position. Does it depend upon the path? Is there any information of the path followed? No, there is no information of path. So it means this work done, it does not depend upon the path followed by the charge. So these type of forces for which the work done is independent of path, these type of forces are known as conservative forces. Okay, so let us summarize this lecture. So we have understood what is potential energy difference, so which is defined as potential energy at final point minus potential energy at initial point, and ultimately it comes equal to the work done in moving the charge from first point to second point and without acceleration. That is important. Then we understood how to define potential energy at a point. Suppose if I have to calculate potential energy at point P, so that will be equal to work done in moving the charge from infinity to that particular point, and that too should be without acceleration. And one more important thing, this work done is by external force, so it will be written as F external dot dr, and we have to move it from infinity to P. But because the known force to us is the electrostatic force, but because we want to keep it acceleration, we want to keep it 0, so that means external force and electrostatic force, they must be equal and opposite. So it means in place of F external I can place electrostatic force as well, and there will be a negative sign. So that is how we can calculate potential energy at a point.